index in a fiery car rescue caught on camera near Auburn, Georgia.
Okay, so this is Ms. Heisenbuttle, and today we're going to be talking about some of the VEX structure and electronic parts that you're going to be using in our robotics course today. So first off, there are three kinds of bearings that we talk about on a regular basis, and these bearings are what's going to hold things together for you. So those are Delring flat bearings, these guys right here, these large ones. Well, they're all about the same size, but they have three holes in them. The holes are round. And so what they allow you to do is to put a screw through them with a Kep's nut on the back and hold them to a metal piece. So it supports a shaft which would go through one of the holes, and the other two would be screwed into the metal part. So it holds it perpendicular, so it goes through the holes. Then you have, basically every time there's an axle that goes through any metal part, you're going to need a bearing to keep it steady and keep it sturdy. Otherwise, your axles will wobble. So every time an axle goes through a metal part, you should have some sort of bearing there to support it. Pillow block bearing mounts, or pillow block mounts, are these guys right here. And they support a shaft off the structure. So the screws would go through the two side holes and the axle would go through the center. This has round holes so that the axle freely turns inside of it, which, is obviously what you want. But it will support an axle as it's going up so that it's like a good ½ inch or so away from the structure, but you can still keep it from wobbling. And then there are these lock bars here. Notice the lock bars have a square hole in the center. And the reason is because that square hole allows them to actually lock onto a shaft or an axle so that whatever you attach the lock bar to will actually turn with the axle itself. So that you can, for example, attach a metal piece to the lock bar and then the metal piece will spin when the axle spins, and it will stop when the axle stops. So we have a whole bunch of different kinds of screws. The primary ones we use for building things are called the 832 screws. They are used for assembly of structural parts. Now, I know the picture shows them as silver. We have some that are silver. We also have a bunch that are black. So just because of the color of the screw doesn't mean that it's one kind or another, because we also have the other kind of screws that are also both silver and black. I know it gets confusing. You really want to look at the head of the screw. The fatter head ones are the 832s, and they are for assembly. You use a 3/32 short arm hex Allen wrench to tighten them. So what that means is a hex wrench has 6 sides on it, and it locks in like a key. Sometimes they're called Allen keys or Allen wrenches, and you spin that to tighten them. And so that's how we tighten up those. They are wider than the 632s. Again, I would look at the head of the two next to each other. You can see the difference. The 632s are actually considered motor mount screws. They're used on motors and the green racks that we have that have they have little tiny screw holes in them. Those are for these much smaller screws. These they're thinner than the 832s, and in this case they would need a 5/64 Allen wrench to tighten them. So the 5/64 wrenches that I've bought are the long arm wrenches. So if it's a longer armed wrench, then it's a 5/64. If it's a shorter armed wrench, then it's the 3/32. So 5/64 is the size of the wrench that goes with the 632 screws. You cannot tell the difference between these screws by color. Like I said, we have some silver ones of both sizes, and we have some black ones of both sizes. And unfortunately, you just can't tell the difference without actually picking them up and looking at the heads to see which one's bigger. So there are ways to attach things that don't involve screws. That would be with these pop rivets. Now, there are two parts. There's an interior part and an exterior part. When you push the interior part all the way through, it pushes these the plastic legs here outwards and locks it into place. So when it's on a piece of equipment, it looks like this. You push in from the metal side. They're pushed in from the metal side, which is basically the back of whatever you're doing. You push it in from the back or the metal side of the connection, and it goes through and then locks into place. And the hold's pretty firm. If you notice that they feel really wobbly, it's because you put it in backwards. So use a screwdriver or an Allen wrench to push the center part back out and flip it around and do it on the other side. So they snap into place and hold bearings without using any screws or any Keps nuts. They are really fast to use, so you can attach things really, really quickly. However, they don't tend to be nearly as strong as putting something together with a bearing and an 832 screw and a Keps nut on the back. These are I would say these should be used in structure where it's not going to receive a ton of torque on it or a ton of pulling. So just make sure that wherever you're using them in a way that best suits them. Okay, so then we have our nuts. We have Keps nuts, which are used to fasten to the back of the 832 screws. You can always attach them so that the teeth are against the metal, so that those teeth are actually correctly gripping the threads of the screw, and the little metal teeth there kind of grip the metal back part. So with that come the shafts and axles. Axles are usually attached to motors or to gears and sprockets. They are square. So the ends, notice, they're not round, they're square, so that they can lock inside of the motors and the gears and the sprockets. And this makes them spin. When you use an axle or a shaft, you have to have 3 points of support. Remember we talked about that earlier. So it has to go through 3 things in order to make sure that it doesn't wobble. Because wobble is bad and your stuff will fall apart. So shaft collars. Locking shaft collars are the silver ones. They go on a shaft and can be locked into place with a 5/64 long arm Allen wrench. So the same one you use for motor mount screws, you use here to tighten this up. So the shaft goes through the center. You never put these on a 832 screw. It strips up the inside and then it doesn't work very well as a shaft collar anymore. So you can also use rubber shaft collars. They're actually not rubber. They're more like polymerized plastic. But either way, people tend to just call them rubber shaft collars. They also go on a shaft. They hold things in place really well, but they don't lock. So they just sort of slide on and off the shaft. So as you can see here, here's a locking shaft collar. If you had one of the rubber ones there, you'd have to be careful because those rubber ones will move around. So if it's going to have a lot of pressure on it, you're going to want the locking ones instead of the rubber ones, but we do have both. The rubber ones are much easier to put on. So in this case, we're going to ask you if you can see 3 supports in the image. So the first one up at the top, up here, we're looking at a motor and a metal bar right there. Then we've got a Delrin bearing right there, which is supporting that same axle. And finally, a metal bar and a bearing on the other side. So there are 3 points of support. the metal bar, the bearing, and then another metal bar and bearing to hold it in place and keep it from moving. Now, if you look down here, there's a second motor. So again, motor and metal bar, bearing, and a spacer in this case. They are using some little plastic white spacers. And then a metal bar and a bearing on the other side to hold it in place. And so that does a really good job of making sure it doesn't wobble. So those are kind of the basics. Now we're going to talk a little bit about spur gears, which are these over here. And spur gears basically have teeth that mesh together in order to transfer motion from one axle to another. Then along with that, we have these slightly, I went too far. There we go. We have these slightly larger spur gears here. Those are the high strength gears. They are double thick gears, and basically the idea is that they just hold these teeth are just stronger and hold together a little better than the regular gears. These down here are at an angle. You can see here they're at a 45-degree angle. So two 45-degree angles make a 90-degree angle. These are called beveled gears because they are at a little bit of an angle there. Then we have sprockets and chain. Sprockets have super deep grooves for the chain to fit into. They transfer power over long distances. They come in a variety of sizes so that you can mess with your gear ratios and get more torque or more speed depending on what you want. And each chain also has a master link system for easy size adjustments. What that means is that you can, with like a fingernail, pry these apart and make these bigger and smaller. So the chains themselves are not to be worn as necklaces, and you're not going to play with them. The problem is that if you're screwing around with the chain, you're going to break it, and we're not going to have any chain. We actually need to build a chain drive. So they only get used for actual robotics, not for screwing around with. Now, we have a cortex. There's a lot about the cortex. Basically, it's the brain of your robot. This is where the core or the code gets stored. Each cortex costs around $250 to $300. And it will break if you drop it, so be really careful when handling it. Here, we're going to ask you to draw some arrows to show in your notebook where the different pieces are. The cortex has 8 analog ports. You'll notice they're labeled right here as analog ports. So go ahead and draw your arrow in. It also has 12 digital ports here. Notice they are labeled digital. Analog is for analog sensors, digital is for digital sensors. It has 10 motor ports, starting with 1 and going through 10 over here on the other side. Again, it is labeled motor. There's a battery connector right here so that you can actually plug your battery in. Right next to it is the on-off switch. So those are the parts of the cortex that you need. Now, we're going to talk about some sensors. We have 2 kinds of sensors. The 2 we have are digital and analog sensors. Analog sensors plug into the analog ports 1 through 8. Digital sensors plug into the digital ports, which are 1 through 12. Digital sensors have 2 states, either on or pressed, which are the same thing. If it's on or it's pressed, then it's on, which is basically a 1, represented by a 1. And if it's off or not pressed, then it's represented as a 0. So you've got, sorry, I keep moving my mouse now, you can't read it. On is 1, off is 0, and that's how it reads its signal when you read it on Robot C. We have digital sensors. We have 3 different types. We've got bump switches, limit switches, and optical shaft encoders. So there's some pictures. So the push button or bump switch up here, this is the bump switch, and it does sort of look like a push button. And it will sense collisions, or you can use it to turn things on and off. This is a limit switch. It's generally used to make sure that a part of a robot doesn't go too far. So this arm of the limit switch here, this arm, when it's pressed down, can turn off a motor, which will save you from tearing up some of your motors. So the other digital sensor that we use is called a optical shaft encoder. It's a little different than the other sensors. It counts the number of degrees that a shaft rotates. And it has a really small light that shines through 360 holes. As it turns, the number of holes that it passes are counted. So inside there's this little light, and it counts the number of holes to show how many times it is spun around. So the digital shaft encoder can actually stop at 90 degrees, whereas the other option that we use for turning an axle is called a potentiometer. It doesn't stop at 90 degrees. That one has more to deal with power and time. So, analog sensors. Analog sensors return one number at a time, just like an analog clock. They give you in-betweens. They give you like a whole range of things, not just 1 or 0. It's not on or off. It's 1 or 0. So depending on the state of the sensor, that number can be anywhere between 0 and 496. Why 496? I honestly don't know. That's just the number that it goes up to for all the analog sensors. In reality, the sensor is outputting a voltage between 0 and 5 volts. But Robot C turns that into whole numbers, which is how you end up with analog sensors giving you between 0 and 4095 or 4096, is because Robot C converts the voltage and then gives it to you that way. So the first analog sensor we're going to talk about here are potentiometers. They read, there we go. Potentiometers read they basically read how much a shaft has been rotated. Like a volume knob in a car would be a version of a potentiometer. The more you turn the knob, the higher the volume goes, or the lower the volume goes if you go the other direction. Measures rotation of a shaft between 0 and 250 degrees. The cortex turns that into a value of 0 to 4095. Internal mechanical stops are supposed to keep this from going all the way around. Unfortunately, if you put a shaft through here and power a motor and just let it run, it creates a massive amount of torque. So the excess torque against those internal stops will break them, which means then you can sit there and spin your potentiometer all the way around. And basically it causes a dead spot in your potentiometer where it doesn't read anything correctly. Now, you can get around by just programming not in that dead spot, but be aware that it does exist on most of our potentiometers because they're pretty fragile. So the other analog sensors we have are called line followers. And let me bring up everything here. So a line follower reads the amount of light that is reflected from the infrared LEDs. So these are the line followers here, and it's reading the amount of light that gets reflected off the surface. So it measures the amount of light. The cortex returns a value between 0 and 4095. Highly reflective surfaces have very low numbers. So that would be white paper would be a pretty low reflective surface, or a low number because it's a high reflective surface. Low reflective surfaces, rough surfaces, or dark black construction paper would have high numbers. The caution here, in order for these guys to work really well, they need to be about 1/8 of an inch off the surface they're reading. So they need to be super close to the surface to be able to read it correctly. If you have them higher than that, they will not read correctly. So make sure you're keeping that in mind. Now, we're going to talk a little bit about VEX motors. We have VEX 393 heavy-duty motors. Doesn't mean they go faster, it means they break less easily. Motors are set by speed anywhere from 0 to 127, meaning 63 is about half speed. Couplers are meant to be used to raise the motor up, and you can see a coupler in this image right here. That coupler is on there, so there's a little tiny axle that goes into the motor, then the coupler on top, which allows it to come up to the same level as the screws, which is how it's going to line up against the metal bar. That way your motor doesn't tilt. If it tilts, then your axle won't be straight and you will get some really interesting motions. So if you're not sure whether the torque of your motor will be too high for what you're doing, so if you're trying to raise an arm on a bar or something, you're trying to move something slowly, you might want to use a clutch. These are these green guys right here. The clutches are designed to brake. So the clutch will brake rather than the motor itself when too much torque is added. So if you're trying to lift something super heavy, put a clutch on there, and that way you won't tear up the gears on the inside of the motor. Instead, you'll just tear up the clutch, which makes the clutch useless after that, but at least you didn't destroy the motor. Clutches are cheap. So motors can be plugged straight into motor ports 1 and 10. So in motor ports 1 and 10, they do not need one of these guys off the side here, which is called a VEX motor controller 29. So motor controller 29 is what the name of this is. When you plug them in, you have to make sure that you either see plastic to plastic or metal to metal. If you don't, then you've plugged them in backwards and you're shorting out your motor, and you could very well destroy both the motor controller and the motor itself. I've actually had a student set a motor on fire doing that because they were running it. They just plugged it in backwards so that it was metal to plastic, and I'm like, what is that smell? And turned out they had set their motor on fire. So don't do that. It applies to extension wires as well that you use with some of the sensors. Like you want your bump switch to be really far away from the mechanism. You'll use an extension wire like these guys here, metal to metal always, or plastic to plastic. If the fronts match up with the metal, the backs match up with the plastic. So those are pretty much the basics. From here on, you should be able to answer some basic quiz questions, be able to tell us what these different pieces are. So make sure you can do all of that and that you can answer these questions in your notebook and be ready for our parts quiz.